All right, this is the last chapter, and this is the first section of that chapter, which is only for HL. They're the only ones that need to know any continuous probability distributions besides the one specific one that everyone will need to know. So HLs, this is for you. We're going to talk about continuous probability distributions, and if you remember at the beginning of the last chapter, we distinguished between discrete and continuous. So for a discrete probability, remember there's a list of numbers that the x's can take on, but for continuous there's a range of x's that the x's can take on. So as far as what the probabilities have to add up to, with discrete, remember they had to add up to 1. Well, if you're going to add up a range of x's, then you need to do what we did in calculus, which was find the area under that curve, and the area under that curve has to equal 1. So that's what makes continuous probabilities valid as opposed to discrete probabilities. All right, let's look at the measures of discrete versus continuous. If I wanted to find the mode of a discrete distribution, I would just look for the x that had the highest frequency. For continuous distributions, then I'm looking for the maximum of the function itself. So I would have to find the derivative of that function, set it equal to 0, make sure it's a maximum, all that stuff that we did when we were doing derivatives. As far as the median goes, you're looking for that number that cuts the list into 2 equal halves, kind of like the middle value. It's going to cut the list into the left half and the right half, or the lower half and the upper half, each half representing exactly half of the numbers in the list. Well, what we have to do with continuous functions is I have to actually, instead of cutting the list in half, I have to cut the area in half, the area under the curve. So I'm starting at my initial x, which I've called a. Normally this goes from a to b. So this will still start at a, but now I've got to stop this area somewhere in the middle, and I'm calling that m. M is going to represent the value of my median. And so I need the area from my starting point to this m, I need that to equal 0.5. So half of the area under the curve. And I'm going to go through an example of how to do that. As far as the mean goes, or the average, I would add up all of the x's times the probability associated with those x's. We did that before. And with continuous functions, I'm doing the same thing. Taking each x and multiplying it by the probability associated with that, which is now expressed in terms of a probability function, f of x. And I'm starting at a, my lowest x, and I'm ending at b, my highest x, in that range of x's. So I'm doing the same thing, but I'm using an integral instead of a summation. For variance, this is the formula that I liked, where I square the x's and then multiply by the probability, and then I subtract off mu squared at the end. Same thing here, I'm going to use an integral instead of all of my x's squared times the probability according to the function, and then subtract off mu squared at the end. All right, this is best looked at with an example, so let's do a simple one. This is an unlikely one where the probability is a line represented by f of x is 1 minus 0.5x, and I'm going over the interval from 0 to 2. And I'm going to find those 4 measures: mode, median, mean, and variance. So I'm looking at this graph. That's what the graph looks like. My mode, remember, is where is the function the highest? Well, that happens right at the beginning, right at x equals 0. So the mode is 0, since that's where the function is the highest. I'm looking at the x value to figure out the mode, not the y value. To find the median, I'm starting at 0, and I need to figure out where, between 0 and 2, where I can draw a vertical line so that that vertical line cuts the triangle in 2 equal halves. So, and it has to be a vertical line too, otherwise it, be pretty easy. So I start at 0, I end at this number m, and I need to integrate this function and set it equal to 0.5, which would be half the area. So if I integrate this function, I get x minus 0.25x squared, going from 0 to m. If I plug m into this function, then all of the x's become m's, and it looks very similar. If I plug 0 into this function, I get 0, so that's what I'm subtracting off. That's why you don't see it. So m minus 0.25 m squared has to equal 0.5. Just using a graphing calculator to figure that out, m is going to be 0.586. So somewhere a little bit past 0.5 is where I can draw that vertical line, and it's going to cut the triangle into 2 equal halves. All right. And now let's do the other 2 measures, which are mean and variance. So I'm going to do the integral of x times f of x, which is x times, there's my f of x right there. Now before I integrate, I do not want to integrate something that's the product of 2 things, so if I can simplify that, I certainly will. I'm going to distribute the x so that I have x minus 0.5 x squared, and then if I integrate that, I get 1/2 x squared minus 1/6 x cubed, and I'm plugging in 0 and 2 because those are my starting and ending x's. Plugging in 2 first and then 0 and subtracting the results gives me 2 minus 4/3 after plugging in the 2, and 0 after plugging in 0, and that gets me a mean of 2/3. To do the variance, same thing, but I've got to square the x's, then multiply by f of x, and don't forget to subtract off your mu squared. I forget that all the time, but don't do that. Same process. Remember, I need to distribute that x squared so that I'm not taking the antiderivative of a product. That's really hard to do. So that's what I'm going to do. It's going to be x squared minus 0.5 x cubed. Take the antiderivative of that and subtract off the 4/9. And after a lot of algebra, then I end up with a variance of 2/9. So that would be your variance for that distribution. Now that's just one example. We will go over more tomorrow. If you have any questions, please let me know, and I'll see you tomorrow.